Good afternoon, everyone. This is ABIR1 and I will be teaching 3 lectures on mechanical design for the course EML3005, and the topic will be indentation as a method of mechanical characterization. So, I am the instructor, my name is ABIR1, and if you have any questions, you can direct those questions to my email, and the email address is given. So, the content of this lecture is in lecture 1, I would talk about the indentation hardness. So, what is the hardness of a material and different methods of hardness test. In lecture 2, I will talk about depth sensing indentation, which is also called instrumented indentation, and I will talk about some of the applications of indentation hardness measurements. In lecture 3, I will talk about a more advanced concept called size effect on the strength of a material. It means if I change the size of a test specimen from macro size towards micro, and further if I reduce that size to nano size, then how the strength of material will vary. So, here I start my first lecture, and the first slide is on what is the hardness of a material. So, hardness is resistance of a material to permanent shape change. So, the key word is the permanent shape change when an external force is applied. So, a schematic of the hardness test is shown here. So, what we do, we apply a force, certain force on an indenter, and it presses on a surface of a material, and due to the application of load, the indenter creates a permanent impression on the surface of the specimen, and that permanent impression is the permanent shape change in the material. What the material does, it tries to resist that permanent shape change, and that is why the hardness of a material is defined as the resistance of it to permanent shape change. So, you have done tensile test in your mechanics of materials lab, and there you have seen that if we increase the strain in a test specimen, the stress increases. So, initially the stress increases linearly along the inclined dotted line. Now, once sigma y, which is called the yield strength of a material, that is reached, the behavior becomes nonlinear, and sigma y, or the yield strength, is also defined as the material's resistance to permanent shape change. Therefore, it turns out that the hardness and yield strength of a material, those are directly correlated, and this can be correlated by a simple expression, which is nothing but hardness is equals to 3 times the yield strength. So, the next point is, therefore, hardness is a measure of strength of a material, which is resistance to plastic deformation. Now, if we think hardness as from the bond perspective, from the perspective of the nature of bonding, we can say that the hardness is result of bonding between 2 atoms, and depending upon the nature of bonding between 2 atoms, the hardness of a material varies. For example, if the bonding is covalent, then the hardness of material is quite higher, whereas for ionic bonds, such as the materials are NaCl, sodium chloride or potassium chloride, for these materials bonding is ionic, and the hardness of those materials is much smaller compared to metals or ceramics. So, the next slide is advantages of indentation testing. So, the first point is indentation is non-destructive, or you can call the indentation testing as a semi non-destructive test. What is meant by this is you do not have to test the specimen till failure, whereas when you test a specimen in compression or in tension, most of the time we test those specimens until failure, whereas for indentation we only just need a surface, a polished surface, and if we have that polished surface, we are ready to perform indents. The second point is only a small amount of material is needed for indentation test. That means only a small polished surface is needed. We do not need any kind of machining to prepare a test specimen for indentation. Next, the indentation testing is useful in measuring mechanical properties at very small length scale, such as thin films, nanowires, MEMS, etc. And it also has a special advantage for characterizing subsurface material properties. There are several loading and deformation phenomena where the deformation is in the subsurface, and what we can do, we can cut and section those regions, and we can perform small indents at those regions to extract mechanical properties. And the most important advantage is, once we know the hardness of a material, we can directly calculate the yield strength of that material by using very simple formula, which is yield strength is equals to hardness divided by 3. So now I am going to talk about different types of hardness measurements. The first type of hardness test is Mohs scratch test. So this scratch test is used to compare hardness of the minerals. So this kind of test are mostly used by the geologists. So in this table you can see that I have listed several minerals and I have listed the corresponding hardness of them. So the mineral called talc is the softest of them and has a Mohs hardness value of 1, whereas for diamond, which is the hardest material available on the earth's crust, the Mohs hardness is 10. So the idea is the harder material will be able to create a permanent scratch on the surface of a softer material. That means gypsum, which has a Mohs hardness of 2, will be able to create permanent scratch on the surface of talc. Now, the second type of hardness test is called indentation, where we perform an indent on a material surface using a tool called indenter. And these indented tips may have various geometrical shapes. Those may be spherical, the tips of those indenters may be spherical, may be conical, or it may have some other geometrical shape. And there are several types of indentation tests based on the geometry of the indenters. So those kinds of tests, these are performed in laboratories and also industrially. So these 3 tests are Brinell, Vickers, and Rockwell hardness tests. So in the next slide, I am going to describe those different kinds of tests. So Brinell hardness test, a schematic of Brinell hardness test is shown here. So you can see the geometry of the Brinell indenter is steel balls or tungsten carbide balls. So the indenters, so we select these indenter materials such as steel or tungsten carbide depending upon the material which are going to test. For if we test a softer material, we are going to use steel balls, whereas if we want to use a harder material, we use tungsten carbide balls. So what we do, so this sphere shown in the figure is the indenter, which has a diameter of capital D, and we load this indenter on the surface of the test specimen. And if we unload this indenter, this loading will cause a permanent impression on the surface of that indenter. And we consider that the diameter of that impression is small d. So if we know this, if we know the values of capital D and small d, we can calculate the Brinell hardness using this formula given below. So look at the expression of hardness. It is the applied force divided by the residual surface area under load, and this residual surface area is measured by imaging in an optical microscope. So in this figure, I have shown a permanent impression after unloading of spherical indent. And what we do, we take that specimen after indentation, we take that specimen under a microscope, and we can measure the diameters of those indent, and that diameter is considered as small d. Now, depending on the materials which we are going to test, we select our indentation load. For example, for hard metals such as case hardened steels, very hard steels, we use F is equals to 30 times d square. So this capital D is the indenter diameter. Whereas for softer metals, we use F is equals to 5 times d square. And for Brinell hardness test, we generally use d equals to 10 millimeters. Next is Vickers hardness test. In Vickers hardness test, we use a different indenter, and the indenter geometry is square based diamond pyramid with included angle of 136 degrees. The hardness test procedure is very similar to the Brinell hardness test. What we do, we have, so this is called the Vickers indenter, and we load that indenter with a certain force F, and if we load and unload, we can see a permanent square impression on the surface of the specimen. What we do, again we take that specimen under an optical microscope and measure the diagonal lengths D1 and D2, and then we take the average of D1 and D2 and consider that to be average diagonal length D. Now, if we measure this average diagonal length, then we can calculate the Vickers hardness number by using this formula. It is interesting to note that again Vickers hardness is defined as applied force divided by the residual surface area under load. So, therefore, the dimension of hardness is force over area, which is nothing but stress. That is why hardness can be directly correlated with stress, more specifically the yield stress of the material. Another important point about Vickers indent is that Vickers indent is self-similar. That means Vickers hardness values are generally independent of test force. That means whatever test force we use for Vickers hardness test, we will get the same hardness value all the time. The third type of test is called Rockwell hardness test, and the steps are, in first step we apply a minor load F naught onto the surface of the indenter, which is transmitted to the specimen, and we hold the indenter at that load for a specific dwell time, which is for a specific dwell time, and we measure the depth, which we designate as H naught. Now, in step 2, we apply a major load, which is significantly greater than the minor load, and we designate that major load as F1, and we hold that load for a specific dwell time. So, in the figure you can see that we have applied a minor load F naught, and the next step we have applied F naught plus F1. So, in step 3, what we do, we remove the major load F1 while still applying the minor load. So, in step 3 you can see that we have removed the F1 and F naught or F0 is still applied. So, what we do, then we measure the residual depth again, which is designated as H1. So, in fourth step we calculate H1 minus H naught, and the hardness value is directly obtained from the dial gauge attached with the hardness tester, which is essentially a function of that H1 minus H naught. So, mainly there are three types of Rockwell scales, and these three types of scales, we use these three types of scales depending on the materials we are testing. So, Rockwell scale A, for Rockwell scale A we use Braille indenter, which is nothing but a 120 degree diamond cone, and the applied load is 60 kilogram force. Whereas, in Rockwell scale B we use 1/16 inch steel ball, and the applied load is higher, which is 100 kilogram force. And for Rockwell scale C we again switch to Braille indenter, and we use a further higher load 150 kilogram force. So, Rockwell scale A is used to test the hardest of the materials, such as cemented carbides. So, cemented carbides are certain kinds of ceramics, and it is one of the hardest available materials. This scale is also used to test thin steels and shallow case hardened steels. So, these steels are very hard steels, whereas Rockwell scale B could be used to test the softest of the materials, for example, copper alloys, soft steels, aluminum alloys, and malleable iron, etc. Rockwell scale C is used to test materials which are harder than Rockwell scale B100, but softer than Rockwell scale A. So, depending upon the materials which are going to test, we select our Rockwell hardness scales. So, here I conclude my lecture 1, and in lecture 2 I will talk about a more advanced concept called instrumented indentation, which is mainly an automatic process and significantly different from what I discussed in first lecture. Thank you.